Okay, so we just finished with similar triangles and talking about how similar triangles have proportional sides. We're going to kind of extend our thinking on that and take the triangle apart into separate pieces, not just sides of triangles. So what we've done here, let's zoom in a little bit. What we've done here is taken triangle ABC, and we've drawn an auxiliary line DE that is parallel to AC. It's not necessarily the mid-segment, it doesn't look like it's halfway up the triangle, but it is parallel to AC. So that's the important thing here, is that we have this parallel, meaning that angle BDE and angle BAC are corresponding, so they're congruent because these are parallel. Same thing over here. These are corresponding, so they're congruent. And then, of course, this one is the same as itself by the reflexive property, or third angle theorem. So we know that these triangles are similar because these lines are parallel. But what we want to do with that here, so we know that that means BE over EC. So that's this side of the short triangle over the corresponding side of the long triangle is equal to BD, I did that wrong, BE over BC, right? We need the entire side of the triangle, or at least we did. And this is going to be BD is the short side over BA is the long side. So that's what we know from similar triangles. But what we're going to establish here with triangle proportionality theorem is that we don't need the entire side. We can actually just look at BE and EC and say that they're proportional, that ratio is proportional to BD over DA. So we don't actually need the entire length of that side. So our theorem says if DE is parallel to AC, then we know that BE over EC, so that's what I wrote first up there, so BE over EC, which are just the two pieces, we don't actually have BC, which is the full length of that side of the triangle, is going to be equal to BD divided by DA. And since our converse is also going to be true, that means this is a biconditional. So if we know that BE over EC is equal to BD over DA, then we can conclude that we have parallel segments, DE and AC. So just going the opposite way, we reverse our hypothesis and conclusion. So let's look at a problem or two. First one, find the value of x. Whenever we have a setup like this, I know that I want to put these two into a ratio and these two into a ratio. Which way around they are doesn't really matter because if I flip this proportion over, it's still going to be true because none of these things are zero. So when I have a situation like that, I like to put the x on top to make sure that I don't have to later bring it up there. So I'm going to set up my proportion to be x over its mate, which is 15, is equal to, now I have to go in the same order here. So I got x was between the parallel lines. So on the other top we have 14, which is between the parallel lines, over 12. So if I solve this for x, then I'm going to multiply this 15 over to this side. Now, rather than multiplying 14 times 15 and then dividing by 12, I find it a lot easier to act like we're just simplifying a fraction. So I see that 15 and 12 are divisible by 3, and I can simplify that to 5/4. And I see 14 over 4 simplifies to 7/2. And now nothing else simplifies, so that means my x value is 35 over 2. So that's going to be what I get for x. And yeah, so then we can move on and look at this one's pretty much the same. Let's scroll down and take a look at one where it's given a little differently. So let's look at number 4. So again, I'd like x to be on top, but this time we don't have corresponding pieces. We have these two segments, but then these two sides of triangles. So kind of the reverse of what we've done before, we're going to subtract here and get 21 for this corresponding part. Then I can set up my proportion to have x over 7 is equal to 21 over 6. And if I solve that, 21 over 6, those are divisible by 3, so I could start off by saying that's 7 halves. And then multiply by 7, I would get 49 halves for x, which you could put 24.5, but I would leave it as a fraction. That's kind of how I prefer. And we'll look at one more on this page. Let's look at one that has some extra stuff with our x terms. So here we do have the right 4 things, and unfortunately I can't ensure all my x's are on top because these two are going into the same proportion. So if I did x minus 1 over 3x plus 1 equals 6 over 21, that should be a true proportion because I took the matching pieces and put them like that. So one thing, we can just do cross multiplication basically. So we're trying to multiply 21 over to here and 3x plus 1 over to here. We would get 21 times x minus 1 equals 6 times 3x plus 1. We could have also simplified 6 over 21 first. It's still not too late. Let's do that. Those are divisible by 3. So we could make this 2 over 7, which makes these numbers a little bit smaller, and smaller is always easier to deal with. This was a 3, right? Okay, so if we distribute, we get 7x minus 7 equals 6x plus 2, so x should be 9. If we go back and double check, we'll see if this is equal to 2/7. So we get 9 minus 1 is 8, and 3 times 9 is 27, plus 1 is 28. If we divide those by 4, we do in fact get 2/7, so we have the right answer. We can check it by plugging it back in. So yeah, that's pretty much how we're going to work these problems. And we can move on to the second part of today's notes, which is going to be, before we get to the next part, we're going to just recap. We've talked about this before, so this isn't new, but it is relevant to what we're doing here to talk about mid-segments. So we already learned about mid-segments of a triangle that we form by connecting each of the midpoints, and that each of those mid-segments will be parallel to the side that it's not connected to, and that it's going to be exactly half the length of that side. So basically we've split into similar triangles, right? So this small one, we made these half, so it's going to be half as long here as well. So nothing new there, just a reminder. Okay, so part 2 of our notes talks about proportional parts and parallel lines. This is just a small extension of what we just talked about. The difference is now we don't actually see these come to a point. So before we were dealing with a triangle where our two transversals were, man, I cannot draw that at all, where our two transversals were meeting at a point and forming triangles. Now that point served an important purpose in that it basically brought them together and gave us these lengths being proportional because they came down to a point. If we don't have a point there and we just have two transversals going across some parallel lines, the other option is, if they don't meet at a point and make triangles, we could have a third parallel line and we can get some relationships there. So if we have 3 parallel lines cut by transversals, and this of course would be true if you add more parallel lines, right? It's at least 3, because what we need is 2 segments on each side. We need BD and DF to be proportional to AC and CE. So yeah, basically it's the same relationship we just saw with the triangles. The difference is we don't actually have a triangle, but that's okay. we still end up with if AB is, these are lines now, there's arrows. If AB is parallel to line CD, is parallel to line EF, then we have this same kind of proportional relationship with the pieces. So we have BD over DF is equal to AC over CE. And you can think of it when we had the triangles almost as being like, sure, there would have been another parallel line here, but since they meet at that line, we don't actually need to see that the line exists like we do here. But it's very much the same exact kind of situation that we had before. So moving on to try some problems, we know that x goes with 52, 18 goes with 45. I would like x on the top, so I'm going to do x divided by 52 equals, and then on this side, the one that matches with x, so we need to be between the same pair of lines. So on our transversal, we were between, let's just give these names, we were between lines B and C, and so is 18. And then 52 was between lines A and B, and so is 45. So if we wanted to simplify, these are divisible by 9, so we could do 2/5 is equal to x over 52. So if I multiply my 52 over to here, nothing up here is divisible by 5, so I'm not going to be able to simplify that, and I'm going to end up with x equals 104 divided by 5. If we change that into a decimal, it would be 20.8. So I would prefer we just leave it as a fraction, but I do want us to have a good concept of what fractional numbers mean. So if I asked you about how long that is, it's 20.8, so it's about 20 or 21, right? That's about the range that it's in, and I can use that as a sanity check to say, well, okay, I went from 45 down to 18, 52 down to 20 sounds about like the same ratio. All right, let's do one that has some x pluses or minuses in it. So let's scroll down and do number 13. Actually, let's do, yeah, so this one, we just need to subtract to get 14 here and take away the 32. So let's go work this one. We have 2x plus 2, x plus 3, 21, 12. So we're going to set up these two and these two, so we'll do x plus 3 divided by 12 equals 2x plus 2 divided by 21. So when we do that, we can see that both denominators can be divided by 3. So basically I could multiply both sides of my equation by 3, and this would become a 4, and this would become a 7. Now I'm going to cross multiply, or basically multiply 4 over to this side and 7 over to that side. That's going to cancel out my denominators and give me 7 times x plus 3 equals 4 times 2x plus 2. And expanding that out, we get 7x plus 21 equals 8x plus 8. Subtract this way to get x by itself and positive, we get x equals, subtracting that, 13. And if we wanted to double check, we could plug that back in and see. So here we would have 16 over 4, that's 4. Here we would have 26 plus 2, that's 28 over 7 is also 4. So excellent, that is indeed the answer. Okay, so that covers our notes for today. There's some more practice to do as well, but that's pretty much it, I believe. We had in your packet, I believe, or your booklet, it has something about constructing segments. If you'd like to do that, I think it's an interesting thing to look at, but I'm not going to go through that in the notes, and we're not going to test constructions. But you can use some of the principles we're doing here to split a segment into 3 parts like this.